let's start with an example. If you consider this function f(x), when x is between 1 and 2, function is equal to 2x minus 1, and the function is equal to 0 when x is more than 2 or greater than 1. Okay, what we want to find, we have to compute expected value of this function, x power 2 plus x minus 2. Okay, we want to compute this. We remember yesterday we said that for the expected value of the combination, linear combination of the random variable, we can write it in this form. We can write it easily. X power 2x minus 2 is equal to expected value of the x power 2 plus expected value of the x minus expected value of 2. We know that the expected value of a constant is equal to that constant, but if we want to show it, we can write it in this form. For example, we know that the expected value of this part is equal to 2. Expected value of the constant is equal to that constant. But if we want to show that how we can prove this thing, really we can write it in this form. We know that for the expected value we have to write 2, the value of the random variable, multiple f(x) dx. Okay? We know that's the constant, we can put it here behind the integral and write f(x) dx, and we know that is equal to 1, then 2 multiplied 1 is equal to 2. Okay? Then we always know that we don't need to calculate the expected value of the constant. The default, we know that the expected value of the constant is equal to that constant. But if we want to prove this, we can show this. Then we have to find the second part of this equation, that is expected value of the x. Similar to this, we can write an integral. We know that the x is between 1 and 2. Okay, then the integral is between 1 and 2. Then we can write it x, random variable, and f(x). And we know that the between 1 and 2, the random variable is like this. Okay? 2 multiple x minus 1. Okay? Then, if you multiply this by x. Okay? If you multiply this x by this, we can write integral between 1 and 2. 2 x2, 2x multiplied x, 2x2 minus 2x, okay, dx. We just multiply this by this and this, and multiply this by this and this. Minus 2x, then we can write, okay, 2x3 over 3 between the range of 1 and 2, okay, minus 2x2 over 2 between range of the 1 and 2. We can easily say that, okay, these two by these two, then as a result we have something like this: 16 over 3 minus 2 over 3 minus 4 plus 1. Okay, that is equal to 5 over 3. Okay, then we showed that the expected value of the constant is equal to that constant, and expected value of the x when we have this function is equal to 5 over 3. Okay? For this part, similar to this, we have to find the expected value of the x2. Okay? Then we know that for find the expected value, we have this equation x f(x) dx, and in this case, x is equal to x to the power 2. Then, and also x is between 1 and 2. Then we can write x power 2 f(x) is equal to 2x minus 1 dx. Okay? Then, similar to the previous one, we can write it in this form: 2x3 minus 2x2 dx. Then we can write it in this form: 16 x4 over 2. For this, it means that we have to write it in this form first: 2x4 over 4 minus 2x3 over 3. Okay, we know that we can say that 1, 2. Then, and also we have to write it between 1 and 2, 1 and 2. Then we can write it in this one: 8 minus 1 over 2 minus 16 over 3 plus 2 over 3 is equal to 45 minus 28, 6 is equal to 17 over 6. Okay? And for expected value x to the power 2, we have this: 17 over 6. Okay, then we, excuse me, 3 plus 4. Then we know all the values, and we can just write it in this form. Okay? Expected value of the x power 2 plus x minus 2 is equal to 17 over 6 plus 5 over 3 plus 2, that is equal to 5 over 2. And you know that this is the expected value of this linear combination of random variables.
Sorry?
No.
What is the class? I was thinking it's other class because I've been waiting.
Yeah, no problem.
I mean, is this the normal venue or because I've been waiting for like 20 minutes?
No. On
I know, but last week it was there and also on OIS, it's still that place.
really?
I mean, it's still physical on OIS.
I think we have to change it because I remember that starting from this semester on the Thursday we have a class here, not in physical.
I think last week Thursday it was in physical, I guess.
No.
After the
I don't.
test. After the test.
I don't know about this, but we have to ask from Chow.
You check your
Yeah.
maps.
It says 1 down 6.
Yeah, physical.
Yeah. Okay, doesn't matter. Then we found this 5 over 2, and we know that the actually is nothing new. It's nothing a new thing here. Okay, just a question. Are there any people on there or not?
I didn't see anybody here.
Yeah, it just-
I waited for like 15 minutes.
Okay.
And,
Yeah, okay, thank you. Okay, we know that it's not new, but we wrote this in this form, but in general, we can write it in this form. If we want to find the expected value of this, we can originally put it here. Let me write it. Nothing really new in this. We could compute this expected value of the x power 2 plus x minus 2 in this form directly as 1 over 2 x2 plus x minus 2 over 2x minus 1 dx. We found the expected value of this linear combination in this form because it's easier for us to solve this. You saw that we just wrote two-line integral and found this, the expected value. But if you want, you can easily put this function here and the function of the x here and find this. I know that's just some multiplication by this and found the integral, but we simply find this by using this equation. The second example Okay. We have a circle like this. Actually, it's not a circle, it's just resistance. You know that we have a current from here, we have a current from here. This current is equal to X. This current is equal to 5. And the value of the resistance is 1 ohm. Or we can write it. We know that the current, let me to find fully this X is a random variable. We know that the average current X is mu X is equal to 1. We know that the mu of X, or we usually call it average of the X that is here is equal to 1. And we also know that average power dissipated over the 1 of resistor is equal to 40 watts. Okay, find the sigma 2 xy that is the variance of the current X. Okay, we know that the average of the X or random variable is equal to 1, and also we know that the power in over the resistor is equal to 40, but we have to find the variance of the X, or we can call it sigma xy. Okay? If we want to find this, first we have to find that how much current is over this resistor. You know, how much current we have, we go to this resistor.
Average 6 amps.
But
Average of 6 amps.
no. We know that we have two currents here, means that the current that will go to the resistor is equal to 5 plus X. we know that we have the resistor by 1 ohm. The power of this resistor, are the 1 ohm resistor is equal to 4, and the current is 5 plus X. Then we have to find the variance of the X. From high school, we know that the power is equal to I power 2 R. Okay? So, in this case, we have R is equal to 5 plus X power 2 multiple 1. Okay? And we are given expected value of the X plus 5 or 5 plus X power 2 is equal to 40, because we know that's equal to 40. Then and expected value of the X is equal to 1, because we know that we know that the expected value and mu is the same. Then we know that the expected value of the X is equal to 1. We know this part from the question. Then we can write it in this form. Expected value of the X plus 5 power 2 is equal to expected value of the, put it here, x2 plus 10x plus 25 is equal to 40. We just wrote in this form. Then we can say that, okay, similar to the last example, we can write it in this form. Expected value of the X power 2 plus expected value of the 10x plus expected value of the 25 is equal to 40. We know that the expected value of the constant is equal to that constant, 25. And for this case that we have a constant and we have a random variable, we can write it in this form. 10 expected value of the X. Okay, 10 multiple expected value of the X. We know this from the theory that we taught last session. Then so you know that expected value of x power 2 plus, what was the expected value of the x? 1. We know that here. 10 multiple 1 is equal to 10 plus 25 is equal to 35. Okay? Means that expected value of the x power 2 is equal to plus 35 is equal to 40. Then we can say that expected value of the x power 2 is equal to 5. And now we know that the expected value of the x power 2, expected value of the x, both of them. Since x is equal to expected value of the x2 minus mu x power 2. We know this, I wrote 5 or 6 session ago. We know that if we want to find the sigma of x, we have to write it in this form. Then we can write it here. 5, we know that the x is equal to, we know that the value of the expected value of the x power 2, 5 minus what was the mu x? 1. Then 1 power 2, that is equal to 1. Then sigma power 2 of the x is equal to 4. And we easily found the variance of the random variable of the x by using this. Just two simple examples of the variance, mean and variance of the linear combination random variables. And we'll continue. We will start with the theorem. Okay. Theorem. If x and y are independent, then we can write it like this. Expected value of xy is equal to expected value of the x, expected value of the y. But just in the case of the x and y are independent from each other, we can easily prove it by this. Again, you are not responsible about the proof, but are just for your information. You know that the expected value of x and y is equal to, because we have two variables x and y, we need two integral minus infinity to infinity and minus infinity to infinity. The first one, the inner integral is for x, the outer integral is for y. Okay? I know that all of you know about this. F x y dx dy. Okay, we just put the x and y inside the integral. Then we can write it in this form: minus infinity to infinity, minus infinity to infinity. Okay, x, y. Remember that yesterday we talked about this. H, y, dx we can just write this in the case of we have x and y independent. It means from here to here, we using independence. Okay, we just use independency of the x and y, and instead of fxy, we wrote gx and hy. Then we can write it in this form, minus infinity, infinity. We know that the inner integral is belonging to the x because we know from the here. Then we can send out the y random variables behind this integral. Then we can write it in this form: a y h y. Okay. X, x, dx. You know, we didn't change anything here. We just put the random variable of the y and its function behind the integral of the constant, because we know that when we have the integral of the x, y is constant from this point of view. Then we put it here. After that, we can say that, okay, this part is equal to mu x, or we know that the mu x is equal to expected value of the x. Okay, and this part as a mu y. Then we have to write it like this: minus infinity to infinity y hy mu x dy. Okay, we just put mu x instead of this integral because we know that it's the expected value of the x. Then the integral is belonging to the y because we know that we have this dy here. Then we can send it behind the integral because right now it's like a constant. It's not a constant, but in this case we consider it as a constant. Then we can write it like this: mu x minus infinity to infinity y hy dy, and from here we can say that it is equal to mu y, or expected value of the y. And finally we can write in this form: mu x mu y. Okay, or expected value of the x, expected value of the y. Let's just prove to show that when x and y are independent, we can write it in this form. Okay. The next theorem is like this: if A and B are constant, then sigma 2 Ax plus B is equal to A2 sigma x power 2. How we can say this with this proof? We know that we can write this variance ax plus b in this form. Expected value of the ax plus b minus mu ax plus b power 2. We know that we can write it in this form. So first compute this mu ax plus b. Okay, we want to show that the sigma power 2 ax plus b is equal to a2 multiplied sigma power 2 of x. We wrote it in this form, then for